um, free shear zones in three-dimensional steady-state flows. This work has been done in collaboration with people from Budapest and Duisburg. You can see them here. This is the outline of the talk. First, I would like to clarify what kind of shear zones I am talking about. Then I will discuss some width and shape properties. And finally, I would like to show you a nice phenomenon in which shear zones mimic the effect of light refraction. What I mean is that the orientation of the shear zone changes at the interface of two different materials. So here is an example of such a free shear zone. The simplest geometry where you can get it is this split bottom shear cell. As you can see, the walls and the bottom plates are moving in this direction, and there is a split line. This is where the shear zone is initiated. So with this split line, we fix the bottom of the shear zone. But otherwise, the shear zone is free to move. In this in a symmetric situation, of course, it will be approximately a vertical sliding plane. Here is in simulation. Don't worry about the walls. This is just a visualization problem. They move indeed. In fact, in the simulation. The color coding here means the two different colors here means nothing, but the red content is important. It means slow velocity. So when a grain stocks between the two moving region, it gets red. So that's how you see the zone where the main shear deformation takes place. So what is important about these shear zones is that they are free in the sense that they are not, their shape is not a priori defined by some confining walls, as opposed to the normal Couette geometry where the shear band or shear zone is follows the inner cylinder. So here we will see examples where the shape can be something more complicated. It is important that the flow is quasi-static, so we don't have rate independence. It is also important because it makes the problem less complicated. That we have steady-state flow, so we don't have to worry about history dependence. Everything is the material is in the critical state. One more thing. Actually, these side walls play no role here, provided they are far enough from the shear zone. Like in this situation, you can imagine that there is an infinitely wide layer. These side walls play no role. What about experiments? If you want to realize this setup, you have to do it in a cylindrical way. This is this split bottom Couette cell. In the last couple of years, a lot has been done in this geometry. For us, it is enough to know that there is such a shear zone that develops, which separates the rotating and the standing part. So as you can see, a disk rotating at the bottom, and the material above this disk is carried along. It is switched off. I will concentrate first on the width of the shear zone. What is interesting here, and what you can see in the measurements, that you have a sublinear scaling. So the width of the shear zone. So this red region is where the shear deformation takes place. The width, what you can see at the top, grows with the filling height, without no upper bound. The exponent here shouldn't be taken too seriously. It can be slightly less than 2/3 or larger, but it definitely above 0.5, so it is not a diffusion like exponent, and it is below 1. So what we see in the experiment, or what they say, I'm not doing experiments, so what can be seen in the experiments is that the flow is very smooth. These are wide shear zones, so they are not the typical 10 grain diameter shear bands. What can we say about the width in the bug? Here the experimental data, what is available in the literature, is not very good. So I will turn to the simulation. In the simulation, it is very easy to measure what's happening in the bug. We performed simulations in this straight geometry, and varied the number of grains between 3,000 and 100,000, and measured the profile, the width in the bug as the function of the bug height. First, what you can see that this z function is different from the function I told you before. What you see at the top as the function of the filling height. It is not even a power law. If you plot the VZ data rescaled with the top width and with the filling height, all data are on this curve, regardless of the actual filling height, and this master curve is a quarter of a circle. What's more interesting is that this result does not depend on the pressure. What you have here. I mean, you can perform this test in gravity, where you have basically a hydrostatic pressure, or you can switch off gravity in a simulation and apply a large pressure here with a frictionless piston. So basically keep the system at constant pressure, and you end up with the same curve. So gravity does not matter in this case. I'm telling this because there were some ideas in 2007 that actually this is the pressure gradient which is induced by the weight of the material that gives rise, that is the reason for this wide shear zone. Basically, that in the gravity case, the pressure disappears here at the top, and this is why the shear zone is widening. So this is not the case we see here. My question is now, is there any theory out there for quasi-static simulations that can account for such a behavior? I mean, you can see that the system is very simple. There is only one length scale coming from the geometry, this filling height. The result is also quite robust and very simple. But I have no idea what is the underlying mechanism that leads to these wide shear zones. So if you have any suggestions, ideas here, I would be happy to hear them. Now I'm turning to the shape of the shear zone. So basically, the shape of this yellow surface that separates the turning and the rotating and standing part. And I'm doing it on the basis of a very simple model. I will assume that we have hydrostatic pressure. I even don't care about the stress tensor. I will just use this color P, and at the same time I'm talking about shear stress. This shear stress is a frictional shear stress. If I am under this limit, the material is sticking, and sliding can take place only if if I reach this limit with the shear stress. So this is not a very sophisticated model, of course, but it is very good for giving us an impression what is going on. If you start with such a model material, you can draw an arbitrary test surface through the material and ask what is the maximum torque that can be transmitted through such a surface. This is defined by these. So I can write up this integral, and I get the resistance of this surface against the driving torque. And this resistance is depends on the surface. Now I can ask which is the surface where the shear zone forms. Of course, this will be within this model. This will be the weakest surface, right? So what I have to do is just take all the possible surfaces that starting from here and somehow divide my specimen in two, and search for the one which gives the minimum torque. So we end up with this variational principle. As you can see, such a frictional model necessarily gives you an infinitely thin shear zone. So this model is not for describing the width. It is for describing the shape, the position of the shear zone. So what I have here is a well-defined variational problem. Everything is defined. So if I take a filling height or a given geometry, a ratio between the filling height and the slip radius of at the bottom, I can get the shape in the form of this function. So if I take this filling height, what you see here is the cross section of this split bottom cylindrical cell. If I take this filling height, I will get this solution. If I add some more material to it, I see that the shear zone moves a little bit inward. If I continue growing with for larger and larger filling height, here something happens. For larger filling heights, this shear zone detaches from the free surface, and I end up with such a closed form. This is the situation where you don't see anything from outside. Everything which rotates is below this cupola-like shape. And so this is what you see indeed in the experiments, at least qualitatively. It was done in Leiden, this experiment, and with this digging technique, they found this two regime. Just one more thing: if you go for larger and larger filling heights, then the shear zone will be pressed down towards the disk. Okay, so we have a very simple model here that can prescribe us the shape of the shear zone. And now I would like to see what happens in the case where I use a simple geometry, but I put two different types of material in it. So I'm turning back to my straight shear cell, and I will apply homogeneous pressure. Again, I imagine that the pressure gradient around this interesting region is negligible compared to the pressure itself. So I have approximately homogeneous pressure to keep the problem simple. And now I will use two split lines at the boundaries, so both ends of the shear zone are fixed, and I'm asking what is the surface that the shear zone chooses in between. This is what I expect, this refraction effect. We will come to that. There are possible geological applications as well. In nature, you have rock layers, different rock layers deposited on top of each other. The shear zone itself could be the geological fault, and this direction of the shearing parallel with the layer is called, I think, strife-slip fault. So maybe there are some applications in the geology. I don't know any specific example though. So now let's check what the simple model tells us about the shape of the shear zone in such a situation. In the cylindrical geometry, we had to minimize the torque because it was the torque that was fixed from outside. Here we have a shearing force, so we have to minimize the total shear force that is transmitted through the sliding surface. In both cases, if I'm talking about energy dissipation, I don't have to make this distinction. If I say that okay, I would like to minimize the energy dissipation, then it is valid for the both cases. But so I can use this as well. These are equivalent, and the minimum dissipation here doesn't have, in my point of view, any thermodynamical reason. It is coming from simple mechanics. Anyway, I would like to minimize the transmitted force, and I end up with this very simple integral. I have to integrate the effective friction over my test surface and minimize this expression. If I can reduce it further if I take into account the symmetry in the sliding direction. So this is just a path integral, and then we can realize that it has exactly the same form as Fermat principle in the geometric optics. So what you have here for Fermat principle, that you can ask what is the path the light beam chooses between 2 points, between the source and the target. And this principle says that it is the path where this expression is has its minimum. And you can easily derive from this expression the refraction law, the Snell's law of light refraction. So as we see that the same variational principle is working in the two cases, you expect the same refraction law. So this is the prediction. What you expect here is the Snell's law of light refraction, only you have to change the usual index of refraction with this effective friction coefficient of the material. And here's a test of numerical simulation. Instead of this geometry, I happened to use this one. It had some technical reasons, but actually this kind of curved walls has no effect on the shape of the shear zone. What is important that you have this split line at the boundary. So I fill this cell with this material. What you have here is one type of material and another type. The difference between them is only in the friction. And I start shearing, and come back a couple of months later and check what I see. And again, these red particles denote the particles which has slow velocity. And you can see in the velocity picture where the shear zone is formed, and this is the long time average of the shear rate. It is also averaged in the shear direction, so you can see that the effect exists. We can perform also a check whether what is the reflection law. This is as you can see in my small system, this is not a very thin shear zone, so it is not. I have to choose somehow. I have to apply somehow this picture, and what I did is I went along the interface between the two materials and searched for the point where the shear rate has its maximum. So I got here this point, and I just connected it with straight lines to the end of the shear zone. In that way, I have alpha and beta, and I can vary frictional properties of the two materials. I can vary the tilt angle of the interface, and just to summarize this figure, I can say that the predicted refraction index is in a very, very good agreement with the simulation data. So in the simulation, everything looks fine. What about the experiment? The only attempt I have seen, I know about, is done in the lab of Scott Franklin, and they use here very long rods perpendicular to this plane, and they do see the refraction effect. They have problems with sliding at the boundary, and often two shear zones develop, but it's very promising. To summarize what you have heard here, I talked about the widening of the shear zone and asked for a theory or possible mechanisms or ideas, and I showed you this refraction effect in analogy with the reflection of light beams. Thank you.
Anybody able to help with the theory for the widening of free shear zone?
I can't, but I have a question. The last talk about those rods, sorry, the last slides about your rods. Can you tell us what is happening? Oh yes, here it is. You see,
don't really know.
And on the right of the picture, there seem to be opposite indices of refraction. I don't understand what's happening. What's the white thing? It's a shear band.
First of all, this figure looked much better on the screen. So what you have here you have rods with this size. I don't know whether you can see them.
See, yes.
And there are two layers. Here is one, and it contains rods with much larger friction thereof.
Right.
They are smooth.
Right.
So what's happening is that the shear zone which is started here wants to spend a smaller distance or path here.
Yeah.
So I can tell you what I expect it is. It is just a figure I downloaded from the web.
Sorry, the right is okay. I mean, it's exactly what you expect. The path on the right.
Yeah.
What happens to the part on the left? You see, it seems on the right.
I can.
If the top layer was more refringent than the bottom layer. On the left, it's as if the top layer was less refringent than the bottom layer. And I don't understand.
I can tell you only what I think about it. I don't know for sure. I see only the figure.
Yeah.
And I think that here the boundary and the friction here between the boundary and the rods is very low. So it is better for the shear zone if it is next to the boundary. So somehow this is the reason why it tends to reach this side wall quite quickly. This is my interpretation, but I don't know. I really don't know.
I feel there's a problem.
Okay, I think we have to move on.